Hello and welcome to SPSS Class 2, the optional part at the end for people that want to go a bit further or a little bit confident with maths. So what we're going to do is we're going to create a new variable using what's called a log transformation. So if you've ever done logarithms at school, you might remember this and why we do it. So it's easier to create the variable and show you why we're doing it than to explain it in detail first, really. So you do transform and it's compute. And there's different ways you can do it, but as a convention, if I'm going to take this variable GDP PC, what I can do is I can use that to make it go over there. I want to do the same thing over here, but it's kind of an L in front of it. And whenever you see a variable that's the same as another variable with an L glued to the front, that means that they've taken the log of that variable. So to make this happen over here, I'm going to have to type whatever the phrase is for this. I have to find it over here actually. LG10, yes, let's forget that. Capital L, little g10, and then in brackets. So, some marshal par. And also plus 1. So L GDP PC, that's the new variable, and it's going to be defined as log 10 of the old variable plus 1. So let's see if that does anything. Yeah, so we've got this log GDP down here. Now what I've suggested is, before we use it, just to get an idea of why we're doing this, use that great explore thing we haven't used for a while. Just have a look at both the variables and see what they're like. And rather than getting a whole bunch of statistics, I just want some plots. And specifically I want histograms, so I'll get rid of all that and get rid of all that, just a histogram. And I want a histogram for the old one and the new one. So I've got the GDP per capita and the log GDP per capita. I'll just look at two histograms and it should be reasonably striking. If I can find it. So that's a histogram of GDP, so highly skewed. So this unfortunately is the same with so many things we care about in the world. The distribution is extremely positively skewed, as we say. Skewed, I did say. Some people with almost nothing. Loads and loads of people with very, very little indeed, and then quite a lot of people with an average amount, and then just a long stream of some people with the masses and masses out here. So it's really heavily unequal, unfair in terms of distribution, which is why the mean gets pulled way, way above the median. So this is a very skewed distribution, but if you take the logs, because of what I said in the notes here, that if you take 10, that gives you 1. Someone's got $10 goes to 1 when you take log 10. $100 goes to 2, 1,000 goes to 3, 10,000 goes to 4, 100,000 is just 5. So all of a sudden these huge differences get shrunk down, so just 1, 1, 1, 1. So every time you multiply by 10, you just go forward 1 instead of going forward by 10,000 or a million or whatever. So it really compresses down, and the more across you are, the more it compresses down. And you can visually see this here, just that it's made the distribution much more even. And as you'll see if you do the stats next year, that a lot of tests and statistics results depend on having this kind of what we call a normal or symmetric distribution. And it works much better with this log form than it does in this skewed form. So that's one reason why we do it. But even without doing fancy tests, if we then use this log to repeat some of the stuff we did before, so and we can do it fairly easy just by bringing up some, actually we can't, because we'll have to reset the graph. So we go back to looking at the straightforward scatter graphs like this, but instead now we're looking at LGDP. So that's the $1.91. Let's just look at the 551. Go straight to that. And the life expectancy one. And the life expectancy one. No, we had that life expectancy and the child mortality, infant mortality one. Okay, so this is using the log GDP. You can see it's much clearer than it was before, that in this range of countries particularly, you can see that there's a clear decreasing pattern here as income increases. a decreasing level of under $1.90 poverty, and same here, but here it goes to a higher level because it's at those higher levels that there's more poverty at the higher levels, whereas there's more poverty at the high levels here, whereas this lower level of poverty doesn't exist so much in these countries that have moved on a little economically. We can still see it makes it more distinct. There is a correlation, a negative correlation there. Similarly, life expectancy comes out really clearly here. It's more kind of linearized. It shows that as you increase income by a certain proportion, then life expectancy almost is still increasing proportionally. It's not tailing off so much. Infant mortality coming down right across the income range, even up to the richer countries. So it does seem to be a continuous decrease in infant mortality with increasing income. And you can simply do, if you do the bivariate correlations again, and just keep it all the same, just grab that one out and stick in the logged one at the top there. You'll find that all the correlations are pretty much the same in terms of direction, but all stronger, because correlation coefficients again depend on a more symmetric distribution of both the variables involved. So here, when you've done that correction for the skewed income variable, you get much higher correlations. It really brings out the relationships between income, poverty, life expectancy, and infant mortality much more clearly. And if you wanted, you could then do the grande pièce de résistance, if you call it that. Just for completion, I suppose. The scatter matrix with everything on it. So using the logged income. So you can see it's some really distinct correlations this time, much more visible. So worth considering that. And finally, there's just one question I put on there, it's a really maths question. Why do we include the +1 in the compute variable? It's because logs are very convenient things, and they give you this nice characteristic of reducing things and smoothing out distributions. It's all very nice. But unfortunately, if you go below 1, the log becomes negative, as you might remember, and the closer you go to 0, the closer log gets to -infinity, and at 0 it's -infinity, possibly +infinity, which is pretty inconvenient to work with. So it's quite often, if there's a missing value in the data, or there is a 0 for some reason, then you'll get a 0 going into the log, and you get the whole thing gives you errors. So if you add 1 every time, it means that even for a 0 value, you're starting from 1, and log of 1 is 0. So that means that all your values start from 1. You don't have to worry about this -infinity stuff, which is inconvenient to work with. And that's why you'll almost always see a +1 when people are working with logs. Okay, so that's something you'll do more on if you go on to do the stats next semester, or next year in year 2, and then beyond. Okay, I hope you found that interesting. For now, thanks for watching.